I'd like to look at the formula for confidence intervals with two proportions. Basically, this is when you have two proportions. We'll call them p hat 1 and p hat 2. Those are my samples from two different populations, the sample proportion from group 1 and the sample proportion from group 2. And I want to come up with a confidence interval. What I'm really interested in is what the difference is in these two groups. Is the true proportion of 1 different than the true proportion of 2? And if it's different, how different are they? So what I'm looking for is this right here. And I want to come up with a confidence interval for it. I'll recall that on my formula chart, it says a formula for a confidence interval is statistic plus or minus a critical value times the standard deviation of the statistic. So the statistic is simply the estimate of what it is I'm looking for. So if I'm looking for this thing in the green bubble, my statistic, my guess for what that is going to be p hat 1 minus p hat 2. The difference in those two sample proportions. Now the critical value, since it's a proportion problem, is z star, the same z star that we've been using. For example, if it was a 95% interval, it's 1.960. Now the real wrinkle comes in on the standard deviation of the statistic. And so I'll take you back for just a second and have you recall formulas we discussed a couple of chapters ago, namely when we were trying to combine random variables. And we said we're not going to deal with them like this, we'd rather deal with them as variance. And so that's really what I'm going to work on right now. But I know that when I do the difference, this is the one that I'm looking for here, the difference in these two proportions, the formula looks like this. That subtraction sign becomes an addition sign. And I can do this if x and y are independent. Now this is the idea that I want to use in this particular case as well. So first, what is the standard deviation of one of the sample proportions? Well, it's the square root of p hat 1, 1 minus p hat 1 over n1. That's the first group, but that's the standard deviation. So what I really want is the variance, so I have to square that. Now the second formula is the same idea, except it's for p hat 2. So it's the square root of p hat 2, 1 minus p hat 2 over n2. And again, I want the variance of that. But when I look at my formula, right here, I want the standard deviation, and what I found here, this sum, this additive portion here, is the variance. So really, I want the square root of all this. Now what I'm going to do, so you can see how I work this, is I'm going to copy this, I think. And move it down here, and so I've got just a duplicate copy of this, and you're going to see what I do with all these different sections. Now I see right here I've got a square and a square root right next to each other, so that square, well, let's disassociate this, and that square root, those two things cancel. And the same idea over here, that my square and square root are going to cancel, and I've been left with this long but perhaps simple formula where I'm just looking at the individual p hats and finding their portion. The key is that I'm going to add them up. And this deal right here is what goes right here, standard deviation of the statistic. So this is my formula for a confidence interval for two proportions. Now if I change this over to a hypothesis test. A hypothesis test starts out with a belief, in this case, that the two proportions are equal, with an alternative that says they're either not equal or perhaps one of them is greater than the other. So when I come up with my z-test statistic, the formula says it's the test statistic equals the statistic minus the parameter over the standard deviation of the statistic. So this is very similar to what I had for the confidence interval. The statistic is going to be p hat 1 minus p hat 2. The parameter is the truth. And so that's just p1 minus p2. Now, if I believe this, then p1 equals p2, which means this portion right here will become 0 and go away. That's all we have to worry about in AP statistics is the equality of proportions. So that portion of the formula will disappear. And then on the bottom, I have a formula that's similar to what I did under this radical. The difference is now I don't have to use p hat 1 and p hat 2. I can use p1 and p2 with a little wrinkle. So down here, I've got p1, 1 minus p1 over n1, plus p2, 1 minus p2 over n2. The catch is I don't really know what p1 and p2 are. I just suspect, or I'm testing the theory, that they're equal to each other. Now, if p1 and p2 are equal to each other, if they're equal to each other, then I can get a better guess. In other words, if p1 represents the proportion among the boys and p2 represents the proportion among the girls, but there's really no difference in the boys and the girls, then I can combine my samples, because there's no difference, and get a larger sample, which is going to be a better estimate of the truth. So in other words, if p1 is x1 over n1, in other words, among the population number 1, it's the number of successes in group 1 over the sample size in group 1. And p2 is the same way here, and hats on there if they're samples. If it's populations, it's not got a hat. Then I can end up with what's called the pooled p-hat, where I combine these groups together and I get x1 plus x2 over n1 plus n2. And for my sample, this would be with hats. So that pooled p-hat is when I combine all my successes, put that in the top of the fraction, and all my attempts, and put that in the bottom of the fraction. And so my new equation is going to have a better guess for what P1 and P2 are, since I don't actually know P1 and P2. And I'm going to end up with an equation that looks like this. The top of the equation is going to be the same as what I've written before. P hat 1 minus P hat 2. And then I'll go ahead and write this part, although we know that in our course that's going to equal 0. And then the bottom of the equation is the square root of P hat 1 minus P hat over N1 plus P hat 1 minus P hat over N2, where that P hat is this pooled P hat. Now on the AP formula chart, they factored out the bottom of this, or the top part of the stuff under the radical. They factored out the P hat and 1 minus P hat so that the radical looks like this. I'm going to draw it for you real quick. The radical looks like this. P hat, 1 minus P hat, and then 1 over N1 plus 1 over N2. I personally don't like that. I know it's mathematically equivalent, but I think it's kind of harder to understand. So I prefer not to write it this way, although it's certainly fine, and it is what's on the AP chart. Now, one final thing, let's talk about conditions with these. The conditions are just like we've done before, just applied to two groups. So each group needs to be a simple random sample. Each group needs to meet the 10% rule, so I need to sample less than 10% of the population. And in each group, I need to have a large enough number of successes and failures to achieve an approximately normal distribution. Some books leave that sufficiently large number at 10, like we've done before. Some books relax it a little bit and turn it into 5 or 7, but it's essentially the same idea. And the final condition, a new condition, is that these two groups have to be independent of one another. Population 1 and population 2 have to be independent of one another, because if they are not, then I can't combine right here. So there's the formulas for two population confidence intervals and significance tests.